Okay, when we ended before lunch, we were talking about estimated time scores. So that was, and there are 5 ways to actually model on nonlinear growth, and that was one of them, the estimated time scores. We could also consider fitting a quadratic or a cubic model. We could also consider fixing the time scores to a nonlinear shape, or piecewise growth modeling, which we're going to talk about, or time-varying covariates. So let's just briefly take a look at how we would do a quadratic model. So in the quadratic model, we have not only the intercept growth factor, but the linear growth factor and the quadratic growth factor, which has got the time scores squared, as you can see from the formula. So you need 3 latent variables to describe a quadratic growth model. And because of that, you're going to be estimating more growth model parameters, and therefore your model would not be identified without at least 4 time points. So you couldn't identify a quadratic model with 3 time points. So the linear slope time scores are, as we have learned earlier, 0, 1, 2, 3. Quadratic slope time scores are just the linear time scores squared. So it's very easy. And if you do a cubic model, you need 1 more growth factor, and it would be the linear time scores cubed. So that's how you do that, if you're interested. We're not going to actually... And then the next 2 slides show you how you would fix your time scores to values for a, for example, logarithmic growth curve. You estimate the time scores as the log of time, such that you get 0, 0.69, 1.10, 1.39, etc. I show that for the exponential also. And then let's take a look at piecewise growth modeling as another alternative. We'll look at that in more detail. Oh, this doesn't go. Oh, okay, you're right. Okay, so piecewise growth modeling is an interesting way to model nonlinear growth if it will work for you. And there's always those little caveats. So what you would do is, if you take a look at the picture, you can see that there seems to be a linear part of the model in times 1, 2, and 3 that have a lower slope than the linear part of the model for times 3, 4, and 5. So you can represent different phases of development by different pieces of the model. And this is one way of capturing nonlinear growth. And each piece has its own slope growth factor. So you have 1 intercept growth factor. You can see here the intercept growth factor would start here. But you have 2 slope growth factors representing the 2 pieces of the development. And one of the strengths is that then you can also have different covariates for different pieces of the growth. So the way that you do this is you have to create time scores for each of the pieces. So for example, the first piece is for times 1, 2, and 3. So the time scores would be 0, 1, 2 for those first 3, and then you just would continue with 2s for the rest. And then for the times 3, 4, and 5, you have 0, 0, 0, and then 1, 2, 3. So you just sort of zero them out, and you hold them at the same there. So when you set up your growth model, you would say, for example, S1 bar, and then Y1 at 0, Y2 at 1, Y3 at 2, Y4 at 2, Y5 at 2, Y6 at 2. And we're going to see an example of that. I'm just giving you a little look ahead here. So that's all you do. It's very mechanical, although it gives you the ability to estimate a more interesting model. Now, if you think about a situation on the left screen, you may have a situation where to me, this is really not a piecewise model. It's more of a sequential model, because you may have two pieces, but they both have different intercepts and different slopes. And so in that situation, you really have two separate growth models. And you would have two intercept growth factors and two slope growth factors. So you might have I1, S1, I2, S2, where S2 is represented by these time scores, or S1 is represented by these time scores, and S2 by those. And we're also going to see a sequential growth model, I think, but I can't remember. So let's take a look at on your left screen here at the example that we looked at this morning. So we have our LSAY data, and in this situation, we're going to have one intercept growth factor and two slope growth factors. And if you look at the bottom, we have time on the x-axis and our math achievement on the y-axis. And if you plot this, you can see that it appears, this is a little bit more of a complex piecewise model than I showed you over here. Here we're saying that the growth from 7 to 8, grades 7 to 8, and 9 to 10 look to be similar, with accelerated growth from grades 8 to grade 9. And we want to try to capture that by having one piece of the model represent growth from 7 to 8 and 9 to 10, and another piece represent growth from 8 to 9. And so if you take a look over here at the how I set this up, you can note that I have two growth models. So I have two bar statements. But they both share the same name of the intercept growth factor, I. So that's because in the piecewise model, we just have one. And then the first one is S1, the second S2. The first one represents mass 7 to 8. So the time scores are 0 to 1 from 7 to 8. Then they stay at 1 between 8 and 9, and then 1 to 2 for 9 to 10. Whereas for the second one, it's 0, 0, because we're starting growth from 8 to 9 for that one, 1, 1. And so the first piece represents growth from 7 to 8 and 9 to 10, because they seem to share the same growth rate. And then the second one represents growth between grades 8 and 9, where it seems to be accelerated. So this is how we would set up our model command for this type of a model. And note also that I have regressed the intercept and the two slope growth factors on mother's education and home resources. So of interest would be to see if the slower growth is predicted by the same covariates as the faster growth, or if there are different covariates. So if we look at the test of model fit, we have 3 degrees of freedom because we've added parameters to the model. And p-value isn't great for the chi-square, but the RMSEA looks okay. But what we're really interested in is to take a look at the regression of these 3 pieces on the covariates to see if the pattern of significance is different. So we can see that for the intercept growth factor, both mother's education and home resources are significant and positive, as we saw earlier. But for the slower part of the growth, neither mother's education nor home resources are significant, whereas for the growth from 8 to 9, both are significant. So this is, if you have a model for which the piecewise fits and makes sense, because there is one problem with this, and that's that the pieces have to start and end at the same point for everybody. So you have to know that the piece goes from 7 to 8, and that everybody then starts the new piece from 8 to 9. So if people are coming in and having that acceleration at different times, then that would not be a good model for you. It's hard to tease that out. I think there is some work being done on that, though. By whom? Okay, he'll tell you when he wakes up. It's time.
That nap was way too short. Now, there's some work by statisticians and others on individually varying change points, and also trying to estimate that change point timing. And there's work by Elizabeth Slate in connection with PSA development over time and prostate cancer. And another recent article that I have a reference of. So if you're interested in that, send me an email. It's a good topic. Now, let's tie this back to where we started this morning, namely multi-level modeling, to prepare for tomorrow morning, where we're going to get into cross-sectional multi-level modeling. And we're going to do that with the excuse of looking at individually varying times of observations and random slopes for time-varying covariates. If you remember, those were the 2 exceptions where SEM, the conventional SEM framework of mean vectors and covariance matrices could not be used. They didn't cover those cases. And so if you look at this picture again, we're now familiar with these formulas, and we're going to look at them in a different notational scheme. We used every symbol there is, I think, to... we used I and S and eta 1, eta 0. Now we're going to use pi 0 and pi 1, because that's what you will find if you read the Raudenbusch and Bright book. But you will recognize it, that this is a growth model, because A1 is a time-related variable, and the multiplier, the slope, is therefore a growth factor slope, pi sub 1 for individual I. So this is what we called S recently, or what I called eta 1 earlier. And over there sits I, or eta 0. And then we also have a time-varying covariate for the first time explicitly here. It is A2 in the Raudenbusch and Bright notation. And we have a random subscript also for that, with subscript I for pi 2. It can actually also vary across time. And then on level 2, we have not only the growth factor of the intercept and slope, but also the random coefficient pi 2, which is not a growth factor, but just a random slope, saying that the time-varying covariates have differential influence on y for different individuals. So this situation then in the hierarchical linear modeling setting is HLM type of setting, takes A1 Ti as data, because we have the subscript I. It's no longer a parameter then in the factor loading sense, but it's data. And pi 2i is quite commonly used in the multi-level HLM type of framework as well. I'll ignore the rest of this slide for now. So you have this situation. If you want to translate now from HLM books, such as Radenbush and Brike's book on the left, to pictures, if you want to stay with pictures, here's what you could do. You have the math scores up there. You have the growth factors I and S here. You have time invariant covariates here, mother's education, home resources, and you can bring in the gender variable here. You have, in this case, CRS 7 through 10 means course taking in grades 7 through 10, time varying covariates sitting here. And the new feature is STVC. It's continuous latent variable, meaning slopes for the time varying covariates. Slope for the time varying covariate. So STVC here is then in the Radenbush and Brike notation pi 2, over on your left in equation 55. So pi 2 is the same as this. It's a variable because it has subscript I on it. It's latent. And whereas this is pi 1, and this is pi 0 up here. Just so you can easily go back and forth between different notational schemes. And then we also have to say, what does a broken arrow mean? We've taken regular solid arrow to mean regressions, in this case linear regressions, be it down here in level 2 or the structural part, or up here, level 1, the measurement part. Now broken arrows should be thought of as assignments. So we're saying that this random slope is assigned to sit here and saying how much course taking influences Math 7 by being multiplied by that slope. You know, just like it says here, if A2 is course taking and Y is achievement, it says pi 2 says how much course taking influences achievement for that individual. So it sits here, and if you don't have a subscript T on pi 2, if pi does not change across time, then it is the same random variable, same random slope for all 4 time points. And that's what this picture shows. Although it could be different for different time points. You know, the effect of course taking could be varying differently across individuals at different time points. But here it says that we have one and the same. So varying across individuals, but constant across time. So that's just assigning that slope to sit here on these paths from the course taking to the outcomes. And it can be regressed on to the time invariant covariates like is shown there. If you do this analysis here, if you first of all focus on this subscript here, I, let's say now that we have individually varying times of observations. We don't have that in the LSAY data, but we're going to pretend that we have that. So, for instance, at measurement location 2, some people are observed in week 4, some people are observed in week 5 or 6. We want to take that into account. And we're then going to put those variables in the data. Just like you do if you use HLM or SAS-Proc mixed. You have the timing of observations for the individual in these variables, A7 through A10. So for this column in the data set, you're going to see variation across individuals. So it's a variable. So that's, you put it as a variable. You know, so this is the alternative way of treating time scores. And then you designate those variables as t-scores, time scores down here. So the program knows that they are time scores. It's a particular kind of variable. Centering, we're going to talk about later, basically subtracting the mean, so the variables have mean 0, the predictor variables, covariates rather. Then the feature is this at option of Mplus. So you have the growth language again, I and S bar, Math 7 through Math 10 are measured at the time points A7 through A10. So instead of giving the time score, say 0, 1, 2, 3, you read it in as data and say that you have measured them at the different time scores. So in this case, there is no variation because it's LSAY. So if you go into the data, you will find that this computer is getting sleepy here in the afternoon. It doesn't react as fit. Hope you're not as sleepy as it is. So in this case, even though we have designated them as variables, this will be in the data for LSAY. A7 will be 0 for every person in the sample. A8 will be 1 for every person in the sample, etc. This A10 will be 3 for every person in the sample. But you can then see that that gives a possibility of modifying the timing accordingly. Now, don't fall asleep on me, okay? Because this is heating up, really exciting here. So there is the, in statistical terms. So in this case, we've now dealt with individually varying times of observations. Define A as data via time scores and use at. That's the whole story. That's one part. Now for the second part, the second complication that makes growth modeling not be able to be done in conventional SEM is the random slopes for time-varying covariates. So therefore, we go to, gotta have the picture. So that's dealing with this now. That's the random slope for time-varying covariates. That uses a bar-like language as well. We say that we regress Math 10 on course taking in grade 7. So that's this line over on the left here. This path, Math 7, is regressed on CRS 7. That's a regressed on statement, but by having a bar and a name, we're saying that that regression coefficient is random. It varies across individuals. So STVC is the random slope in the regression of Math 7 on course taking 7. And in this case, we've said that it's the same STVC for all 4 of these. It could be STVC 1, 2, 3, 4, but here we have the same to reflect the figure. And this particular construction, this is the random slope construction that you will see tomorrow when we go multi-level in a cross-sectional sense, students within schools. When you have random slopes, you use this approach. So it's the same thing. It's a preview of that. And then you have to add type equals random. To be able to do this, you have to say random in the analysis type. And if you don't, the program will tell you. But otherwise, it's just the same. You regress INS on the covariates, and you regress STVC on the covariates. So it's an interesting construction. If you look at it from a psychological mediational point of view, which I don't think is stressed very much in the multi-level literature, you really have an interesting mediation here. It's like home resources may influence the slope, which influences how much course taking influences Math 7. So it's an interaction here. Well, STVC is the mediator, but that turns into an interaction between home resources and course taking 7 in their influence on Math 7. So you have a predictor of the slope. Slope sits here. So the predictor of the slope plays in here, and then this gets this slope gets multiplied by that, which means essentially you multiply these two, if you focus on those two, in their influence on Math 7, an interaction. Or a mediation through the STVC latent variable. So in terms of mediation of modeling developments, there's a lot more that can be done, and it will be done probably. But this is done standard multi-level modeling by SAS-Proc Mixed or HLM or MLWin or your favorite program, but done then in Mplus using the latent variable approach. And here we get the up. We have twice as many people because we have the females in there. Note that now we don't get any overall test test of model fit, we get the log likelihood value, which is very useful because we can work with neighboring models that are similar but only differ in a couple of parameters. And we know that log likelihood, 2 times the log likelihood difference between the models is chi-square distributed. We talk about that a lot in day 1 at least. With number of parameters for that chi-square test equal to the difference in the number of degrees of freedom for that chi-square test equal to the difference in the number of parameters of those 2 models. So although in an absolute sense this tells you nothing, when you compare to other models it will be helpful. Number of free parameters, you have to keep track on how many parameters you have, and sometimes Bayesian information criteria, BIC, will be useful. But we're not going to focus on that right now. So how do we read this? We have then I and S regressed on covariates. We know that already. So let's focus on STVC, slope of the time-varying covariate. And we look over here, and this is approximately normally distributed test statistic. Just to remind you, so you want to compare to 1.96. If it's greater than 1.96 in absolute value, it is significant on the 5% level. In a new version of Mplus coming, we'll even print the p-values for you. But STVC on home resources is significant. So how do we understand that? Well, that says that it's positive, right? So as home resources increase, the STVC variable value will increase. It's expected to increase. STVC value increases means that the slope is bigger. As home resources increase, slope is bigger. Bigger slope here means that you get more bang for the course-taking buck in terms of the achievement outcome. So course taking has more of an influence on the student's achievement when the student comes from a home with a lot of home resources. Maybe they get help with doing their homework. So that's very interesting to know. What else do we see here in this output? Well, you may want to know, so higher slope is higher for higher home resources, but what is the average slope value? You know, this is a variable. We want to know what the mean is, and maybe what the variance is. At least what the mean is. Is it positive? Well, then you look at intercepts here. Mplus reports intercepts because STVC is a dependent variable. So the parameter in question here is intercept plus the slopes. It's not the mean of this. You can get the mean of this by asking for Tec4 in Mplus, but it's not, the mean is not the parameter that you estimate, but the intercept. However, if the covariates have been centered, and we're going to talk about that a little bit more tomorrow, but it's very simple actually. If the covariates have been centered, meaning that they have been standardized to have mean 0 in the sample, well, then we know that the intercept of STVC is the same as the mean of STVC. So let me say that again for those of you who are not into technical matters. We have agreed that this is a linear regression of STVC onto the covariates. A linear regression is equal to an intercept plus the slopes times the covariates, right? So the mean of the dependent variable, of this variable, is therefore, the mean of this is therefore equal to the intercept plus the slopes times the means of the background variables, of the covariates. But if the means of the covariates are 0, then the mean of this variable is directly equal to the intercept. Okay? So therefore, and we did do that centering. It's called grand mean centering, just in line. You saw that in the input in the beginning, just in line with the multi-level literature, and therefore the intercept parameter, which is estimated, is the same as the mean of STVC. So it is positive and clearly significantly different from 0. So it's good. Course taking helps your math achievement. You didn't need modeling for that, right? But here you got it. Now, for people who come from the SCM CFA factor analysis world, they get a little bit perturbed by the fact that in these models, which have like a random slope like this one here, they don't get any overall fit measure. They don't get an overall chi-square. They don't get the usual CFI, TLI, RMSEA, all of these which are SCM, structural equation modeling terms. So they don't know how to deal with that. And the reason they don't get it is what's explained in equations 100 to 103 here. So we were looking at this regression model where the regression coefficients vary across across individuals. X was time here. In particular, we have a random slope. So here is just a technical side excursion for why you don't get an overall test of model fit. You have a random slope. Therefore, the variance of y is equal to the variance of y given x is the variance of beta, the random slope, times x squared, which is a fixed coefficient, so you square it, plus the residual variance for epsilon, which is theta. If beta was not random, if beta was fixed, this term would be 0, and this term would fall out, and you would only have the usual theta. But given that you have this random slope, the variance of y varies as a function of x values, which implies that you have not only one variance, but as many variances as the x values. So if you're familiar with SCM, where you fit to sigma covariance matrices, you have not one covariance matrix. So therefore, you don't get the chi-square test to covariance matrix naturally coming out of it. So to make a long story short, when you have random slopes like this for time-varying covariates, you don't get overall test of model fit. And you'll see the same thing in the multi-level setting as well. And here already we point out that Mplus allows random slopes for predictors that are not only the usual observed covariates, but it could be observed dependent variables and continuous latent variables. Quite unique strength there. But that's a topic for more advanced models. Should we talk about this slide? I think not. This is covered in the user's guide, so I don't think we need to talk about it right now. And thereby, we get into advanced growth models. And we are in our list of advantages. We're going to walk all the way down through to this and leave the last bullet for another occasion, like tomorrow afternoon. So we have moved down from flexible curve shapes, estimating xt parameters, to individually varying times of observations. And now we're going to talk about regressions among random effects. So just to remind yourself, here is the level 1 model that we use for growth modeling, back to the eta 0, eta 1 notation. Level 2, the variation in the intercept and slope is explained by W. But you notice that the random effects in these models are always on the left-hand side of the equality, never on the right-hand side. You could instead imagine that the growth rate is a function not only of background variables, covariates W, but could be a function of the starting point. So how much you learn from this day to day could depend on how much you knew in advance, how much of these prerequisites we mentioned you actually had time to go through. So a measure of this says that you could have the growth rate dependent on that starting point, not only on your other background variables. So this is then, this equation 4 is connected with this picture. So you see that you have a regression of eta 1 on eta 0, whereas here, in the model that we talked about so far, there's no regression among eta 1 and eta 0. They are joint dependent variables, So it's a two-variate dependent variable system here. But you don't say that eta 0 influences eta 1. But here on the right you do, following. So this is equations 2 and 3 here on the left. And on the right is equation 4. Excuse me. So what's the benefit of that? Well, this may be much more substantively meaningful. In fact, it may be that this effect is insignificant. All the effects of background variables may go through the starting point. Starting point then influencing the growth rate, so there's no direct effect from background to growth rate. You can't really specify that here. So I'm saying this coefficient could very well be significant, and this could be insignificant. This could be insignificant while this is significant. Because say that the true model is a model where W does not influence eta 1 directly, but only indirectly via this mediator. You might still find, if you test this model, that this effect is significant. So in a sense, this is more informative and more to the point, perhaps, in substantive applications. Although statistically you cannot tell them apart. There are certain models that are equivalent statistically. You have just as many parameters here as you have there. 1, 2, 3, 4, 5. And here you have 1, 2, 3, 4, 5. So it's just a reparameterization, as they say. So you get the same test of fit of this model, same likelihood. In some models, you can tell the difference. For instance, I think it would be very hard to, in this scheme, it would be very hard to fit a model which left out the direct effect like that. So this is a hallmark of coming from the latent variable area of structural equation modeling, where you typically do regressions among latent variables. That's what SEM is all about. The structural coefficients in the so-called beta matrix of Uriskog's literal system is all about doing these kinds of regressions. And they should be done more often, I think, in growth modeling as well. Because I think it's very often relevant to, for instance, talk about the speed of learning or development depending on where you started. Here's another version of that, more advanced version of that. So now we again say that growth rate is influenced by the starting point plus some background variable. But now we add a twist to it. We're being more explicit about how this happens. We're going to say that your growth rate depends on your starting point and your background variable and an interaction of the two. So you have an interaction between the background variable math course taking in grade 7 and the initial ability in math that you have in grade 7. And that interaction is marked by this filled circle here. These two variables come together in influencing S. So you have the main effects, beta, B1 and B2, main effects, and the interaction effect, B3. It's an interesting interaction. Interactions in regular linear regression, you take x1 plus x2, and then you add x1 times x2 as a third variable. And it's absurd, so you could just create that variable. But here, one of the variables that interact is a latent variable, the random intercept. Not only that, but it's also a dependent variable, not only an independent or exogenous variable, but it's a dependent variable in the regression. So that can be done in Mplus if you're interested in that. And this is more of an overview description. And we have to wait for our computer to wake up again. Maybe they can restart the computer at the break to make it a little bit more snappy. Okay, so what's done here is using the growth model language again, and here now we're getting away from the at statement and back to where we started. fixing those time scores according to linear. Then we do a little extra overriding the growth language default. Linda talked about two parameterizations, which is having 0 intercepts versus having 0 growth intercept factor mean. Here we switch from one to the other. So we're going to hold the intercepts equal across time and fix the intercept factor mean at 0. Whenever you have interactions, they are easier to interpret if the variables have mean 0. So we can center math course taking in the sample, but here we have to do it by the parameterization. That's sort of an aside. More interesting is that we create an interaction, again by the bar statement, again by type equals random here. And interaction uses then the xwidth option, xwidth. So we cross I with math course taking 7. We multiply I by math course taking 7. So technically this, for those of you who are interested in the technical parts, this is done by the EM algorithm. The latent variables are treated as missing data. I is estimated in the iterations, and I is multiplied by math course taken in the iterations. And then you regress S on I and math course taking. These are the two main effects. And the interaction. Down on slide 124. So that's a latent variable interaction, and this draws on maximum likelihood estimation. And there was an article in Psychometrica by Andreas Klein, who outlined maximum likelihood estimation with interaction between latent variables. So you get results like, and I'll show you that reference in a second. You get results like this. S is regressed on I, and the interaction, and on math course taking. So math course taking has a positive significant effect. I has a positive significant effect. Starting out doing well in math influences how fast you grow. Taking math courses influences how fast you grow. But then you have a negative interaction sign here. Negative interaction. And interactions, require a little bit of work to interpret, particularly if they're negative. So on the next page, I've actually outlined the details of that. And that draws on the Klein and Mossberger Psychometrica paper. And I don't know if I should take time to go through that. Maybe not. Since this is more informational. But in any case, interactions can be reconceptualized as moderation. And that's what this slide is about. And this slide shows in detail then how you can interpret that kind of an interaction result. But I'll just give that as an aside. So if you get to this kind of model and want to do it and think that these slides were not sufficient for your understanding, email Linda. And that brings us to your topic.
I did this one, don't I? Yeah, I did. Okay. So, where are we? So now we're going to talk about a model that has two processes, two growth models in it going on at the same time. So things that were measured at the same time. And that's the multiple process bullet that Bengt showed. And I've mentioned this before. We can have parallel processes or sequential processes. Parallel being when they occur at the same time, sequential when one occurs prior to the other. So when you're going to model with parallel processes, as with everything, it's best to do things in a stepwise fashion and get the growth model for each process to fit independently of each other. Fit the two growth models without covariates and get well-fitting growth models. You can then add covariates and make various model modifications. and only then would you put the processes together. Now, we found that a couple of problems people run into when they put the processes together. One of them is sometimes the outcomes are measured on very different scales. Like one has variances of 1, one has variances of 1,000. So that can cause convergence problems. So you want to, it isn't always a problem when your variances of your variables don't lie between 1 and 10, but sometimes it is. And so if you're having a problem, that's always a good thing to look at. And another issue when you put two processes together is sometimes you need to add residual covariances between the outcomes of the two processes at each time point. So the residual variance of outcome 1 at time 1 and outcome 2 at time 1, you would want to add a residual covariance there. Sometimes you get a message that your growth factors are correlated greater than 1, and that's usually because your model needs those residual covariances. And that's something we could probably add to this slide. So we're going to, once again, take a look at the LSAY data. And what we're going to do is not look just at means, but also the attitudes toward math measured in grades 7, 8, 9, and 10. So they were both measured at the same time. And Bank showed you this earlier. So we have the increase in math achievement scores over time and a decrease in math attitudes over time. So let's take a look at the path diagram for the parallel process model. So at the top, we have the math diagram that we've been looking at, math 7, 8, 9, and 10, an intercept growth factor and a slope growth factor. At the bottom, we have the math attitudes measured at 7, 8, 9, and 10, and we have a linear growth model with an intercept growth factor and a slope growth factor for math attitudes. And then we have regressed all 4 of the growth factors, the solid lines, on mother's education. And we then have some residual covariances in the picture too. So this is an example of the parallel process growth model. Another way to think about this data could have been to consider the math attitudes as time-varying covariates. So there are sometimes when you have a situation where you could have parallel processes, another model you might want to consider would be a model where the other process is treated as time-varying covariates. But in this example, we're going to look at them and treat them as two separate growth processes. And we want to take a look at the input. In the variable command, we now need to add attitude 7 through attitude 10 to our list of on the used variables command because we're including more variables in the analysis. So that's one difference between what we've been seeing. And then in the model command, we have to specify a growth model for each process. So we have IM, which is the intercept growth factor for math, SM, the slope growth factor for math, and we are in this situation having estimated time scores for math 9 and math 10 and fixed time scores for 7 and 8. For math attitudes, we have the intercept growth factor for attitudes, slope growth factor for attitudes, and we're fitting a linear model. So our time scores are 0, 1, 2, and 3. And then we can use the list convention to say IM-SA, which includes IM, SM, IA, and SA. All the growth factors we're regressing on mother's education. And as always, we show the alternative language at the bottom. So we have, as usual, our tested model fit. But what's of most interest in these results are whether the effect on the covariates. So we can see that that mother's education is significant for the math intercept and also for the math slope. However, neither of these, mother's education covariate is not significant for either the math achievement intercept growth factor, the math attitude intercept growth factor, or the slope for math attitude, the slope growth factor for math attitude. So that particular covariate did not explain any of the variability for either where math attitude starts or the growth for math attitude. We also included the residual covariances among all of the growth factors, and you can look at those. So for example, we won't go through all of them, but you can look at the IA, which is the math attitude intercept growth factor, and IM, which is the math achievement intercept growth factor, and you see that they have a positive covariance. So as one of them increases, the other seems to increase. So if you do better on math, you're going to have a better attitude toward it. And then you can go through and look at SM and IM. Well, let's see, where's SM? So SA and SM does not have a significant relationship. So the growth in math attitude and the growth in math achievement don't seem to have any type of a relationship. That's not significant. And then you can look at the other ones or whatever might be of interest. And in a model like this, you can also regress, have random coefficient regressions, just like Banks showed you earlier. So you could regress the various growth factors on each other in a way that you might find meaningful based on what theory suggests would be happening in your particular substantive area. And then I think we're ready for modeling with a preponderance of zeros. Did you make a note?
Yeah, so we try to jazz it up towards the end of the day so you get maximum stimulation here. And modeling with zeros. So this has already come up in the discussion. We are here moving down quickly down the list of advantages of being in the latent variable framework. And here, this responds to the question we had earlier. You have two situations here, outcome variables with different kinds of distributions. Let's say that we focus on the left picture. It's a histogram of a variable. Let's say that we treat it as continuous. It's just categorized into these 1, 2, 3, 4, 5 bars. And it is non-normal, but this is the kind of non-normality that we can easily handle by just using robust, non-normality robust standard errors and non-normality robust chi-square. So this kind of outcome, if you want to treat it as continuous, would be just fine as long as you use MLM or MLR as your estimators, both of them robust. Robust against normality. And I'm saying that it fixes up the standard errors and this chi-square. What about the parameter estimates, you may ask? Well, okay, if you want to know. They are fine even without doing anything. So maximum likelihood parameter estimates are very robust in non-normality. It's the standard errors in the chi-square, namely the inference, that is hurt by non-normality. So that's why you have to have non-normality robust versions of standard errors and chi-square, whereas the regular ML has the same parameter estimate as the MLM and MLR. The parameter estimates themselves are the same. Now, when you have a situation on the right, still wanting to treat the variable as continuous, you have a problem because you really have a non-normal outcome here. You really would need something special to deal with that. And when you really need that technique, it doesn't work. That is, when you really need a robustness against non-normality, it won't work. Satora-Bentley chi-square, the robust, non-normality robust standard errors will not be doing the job for you because already the parameter estimates are going to be off. Already the parameter estimates are going to be wrong in this case because it's probably not likely anymore that a model with linear relationships will capture this big piling up of zeros, this preponderance of zeros, this floor effect here. True, you could treat this variable, say that it was a 5-point Likert scale, then you could treat it as an ordered categorical or an ordinal variable. You could do that, and then there wouldn't be a problem to have a floor effect. There's no assumption of the ordered categorical ordinal model of having to avoid piling up of zeros or piling up at 4. That's fine with categorical outcomes. But then you would have to treat it as a categorical variable, even if you believe that it really was continuous interval scaled out in the right tail. But it wouldn't be wrong, essentially. It would be more complicated and would not acknowledge any continuous part of the variable. So, and it also could be a count variable. You know, you can count how many times in the last 30 days did you sit down and drink 5 or more drinks. Heavy alcohol consumption, for instance. So it could be a count variable, 0 times, 1 time, 2, 3, 4. If it is a count variable, you may fit the data perfectly by a so-called Poisson distribution. But very often when you have a high floor effect in count variables, do you need to take that into account by a so-called zero-inflated model, ZIP, zero-inflated Poisson. And Mplus allows both of those two alternatives, Poisson or zero-inflated Poisson. And we may touch on that a little bit as the days go on. So all in all, we want to tell you that you don't have to be embarrassed when you have data like this. You don't have to hide it anymore. You can actually acknowledge it and say, I know how to do this right. And to do it right, you have to have a model that really specifically addresses the high piling up here. And you can do that in a couple of different ways. Censored normal modeling says that your variable is normal, but it has been censored at 0. So you can imagine that there is a tail to the left of 0, a sort of a propensity that happens to be too low for you to see any action. And that's been used in econometrics, propensity to purchase durable goods in a certain year, you know, like refrigerators. The propensity turns into action when the propensity gets above 0. And then the propensity is equal to the amount spent. But you can have a propensity that's very close to purchasing, that is, your income is almost enough to afford that refrigerator, or you can be far away from affording it. So the idea is that you have a tail here that has been smashed up into this pile. That's a censored normal modeling. Then you have a new kid on the block, relatively new, 2-part modeling, semi-continuous modeling. Came up in health insurance experiments at the RAND Corporation in Santa Monica. Naya Duan and Manning and others worked on that. And recently it was extended to growth modeling by Olson and Schaefer in a JASA article, Journal of the American Statistical Association, which, although it's technical, has a very good introduction and application where they point out that the censored normal modeling is limited with limitations that are avoided by the 2-part modeling. And I'll get to the limitation in a second. But we also have these mixture models, latent class type of models, and the zero-inflated Poisson that you mentioned is one example. Zero-inflated Poisson, just very briefly, in the alcohol setting, says that you have 2 kinds of people. People who don't drink alcohol and people who drink alcohol. People who don't drink alcohol are at 0. They never drink more than 5 drinks in any one sitting. And then there are people who drink alcohol but may not do so, may not drink 4 or 5 or more drinks in the last 30 days. So they can also have 0. So it's a mixture. The zeros come about from a mixture of people. People who don't drink at all, people who drink but didn't drink that much in the last 30 days. So it's a mixture idea. Our first latent class idea in this course comes up in the zero-inflated Poisson. So among those who actually drink, the frequency of heavy drinking is still then characterized by Poisson, but then you have the addition of zeros from those who don't drink. So that's the general idea between zero-inflated mixture Poisson or ZIP. And there's a nice JAS article on that as well. And there are other variations on that theme too, but those are the most important ones. Now, if you look at this, the two-part modeling, which might be particularly accessible for us, it starts out with an original variable looking like this, high piling up at 0. And actually, I'm going to put it on both pages. High piling up at 0, and what is done is to break this variable up in two parts, hence the word, two-part modeling. One is dichotomizing it so that those who don't drink at all, those who had 0 frequency of heavy drinking are here, same people. And all of those who had non-zero, these piles lumped together as having experienced heavy drinking in the last 30 days. So dichotomization of this variable. And then for those who are in the category of having been heavy drinkers in the last 30 days, how frequently they were heavy drinkers is recorded up here. So this is frequency of heavy drinking here among those who drink. Among those who have positive values, I should say. I slip into the two-class thinking. I shouldn't do that because two-part modeling is not two-class modeling. So once again, say that this is frequency of heavy drinking in the last 30 days. You split it up into people who did not and those who did. And among those who did, how many times did they do it? So this tail up here is exactly what you have here. And the only twist is then that, of course, you cannot have any observed frequency up here for those people who were in the 0 category, right? Those who didn't engage in it, well, for those you have no frequency. So for those who have 0 here, you score that variable as missing. As missing. Like 999. And therefore, those people will not contribute to that variable. And then, lo and behold, we have a parallel process model. That's why it comes right after the previous topic. You have the continuous outcome up here with its growth model. And you have the binary outcome, which we call U by Mplus nomenclature. Binary outcome showing did you or did you not engage in that activity. And we haven't talked about growth modeling for categorical outcomes, but it is very analogous to growth modeling for continuous outcomes in that you talk about individual differences in development over time, but it's individual differences in the probability of engaging in the activity. So it's not the value, but the probability that's different across different individuals. So you have a linear growth model for the probabilities, or rather a linear growth model for the logits behind the probability. And the logits, that's a phrase that we're going to connect with logistic regression, which is going to be brought up tomorrow. And that's why we urged you to remind yourself of logistic regression a little bit, although we'll give you a chance to catch up tomorrow. But it is a parallel process model, continuous outcomes combined with categorical outcomes, two growth processes. And like Linda said, there are three ways these processes can correlate. One is through their common influence from X. Two, through correlations between the growth factor residuals. And as Linda pointed out, you may also want to correlate the residuals, except in this case, it's a little bit more tricky when this is categorical. But if you had continuous outcomes, you could correlate the residuals at each time point. So three ways that the two processes can correlate. And they do correlate quite a lot. You know, if you think about this process as the propensity to engage in this behavior, if the propensity is high, the amount may also be high. And if the propensity is low, well, then the amount, if they had engaged in it, would be low. And getting back to the point, why is this better than censored normal modeling? Well, because we have split the process in two parts. Therefore, covariate influence can be different for this part than for this part. Coefficients here and here could be different. So the determinants of engage in the behavior may be quite different from the determinants of how much you engage in the behavior. That's a great strong point of this modeling, and that's what Olson and Schaefer emphasize in their writing. And we have an interesting paper on the Mplus website by University of Washington group. Rick Brown and others wrote a paper using Mplus to do this kind of modeling where X was an intervention, a randomized intervention. And the intervention had different effects on the propensity to engage in the behavior rather than in how much they engaged in behavior. And if I remember correctly, one was significant and the other wasn't. One effect was significant, the other wasn't. I can't remember which one it was. And we have worked on this quite a lot to make it easier for people to do this because we thought that was such a great idea that Wilson and Schaefer had, that we developed a language to do this data splitting. And we can go forward to that. And there are two parts. One, the pages that you have, starting on slide 151, shows you what is done and what you had to do yourself until we came up with this automatic feature in Mplus. The automatic feature is called data two-part. Data two-part. And that automatically starts from a variable here, AMOver, meaning alcohol misuse overall. And when the value is greater than 0, Mplus goes and scores U, the dichotomous part, as 1, and Y will have the value of AMOver, which is greater than 0. If AMOver is 0, if you're at the floor effect there, it scores U as 0, and Y becomes missing 999. If the original variable is 999 and you're missing, you have missing on both. It proved to be too complicated for people to do this without making mistakes, including myself. So we decided to come up with this language, data two-part, which automatically goes from this variable to these two variables. And then you can go directly and specify your parallel process growth model for that. So we can skip over step 1 here and go straight to step 2. And then we have the use variable statement. We have a bunch of U variables and a bunch of Y variables, you know, for the lower and upper part of this bivariate process. And you have defined missingness, particularly on Y. You're going to have a lot of missingness, right? You have missingness whenever U is equal to 0. And one thing you should remember that's very important in Mplus version 4, what will be changed in Mplus version 5 is this statement, type equals missing. Type equals missing says that you're going to take the best approach to dealing with missing data, namely the MAR approach. And if you didn't say type equals missing here, but designated people designated this missing data symbol, people who have that missing data symbol on any of the variables will be deleted. List-wise deletion would take place unless you had type equals missing. And of course, in this case, you have a lot of missing on Y. Whenever U is 0, you will have missing on Y. So you really need to use type equals missing up here. And what I was alluding to is that now in version 5 forthcoming, type equals missing is going to be the default. So people don't even have to think about that. But in any case, this we have examples of in the user's guide, including Monte Carlo simulations for it. But all it really is a parallel process model using the bar statement. And then you can regress all of these growth factors, IU, all the way down to SY on a background variable here, on a covariate. So that's a pretty interesting idea for really taking seriously the modeling of the zeros. So then you can include the people who have not yet started to engage in the behavior at a certain early time point. You don't have to delete your sample. You don't have to transform your data. You don't have to worry about non-normality robust techniques. You model it. Now, there's a little bit more modeling effort here, because you have two processes. And as Linda said, you would then first want to do a growth model for each of the processes separately. First for this, for PAPS, which is a binary growth model, and for this, the continuous model, and then jointly. So it's a little bit more work. And interestingly, this carries over to multi-level settings where you have, say, students within schools, and also into growth mixture modeling where you have different trajectory classes. But I'm going to skip that. And we have now come to multiple populations. So now we've come to the point where we are ready for some questions again for you. And then at 3 o'clock, we'll take a break. How's that? So let's see. Who can come up with a question? The lady in the back. Slide what?
146.
146?
Where you show how you split the data into the propensity versus the counts. And I was just curious on the counts, they're still technically skewed.
Say that you were concerned about what?
Well, they're still technically skewed. So would you have to use the Centaur bent or...
Oh, you're talking about this here.
Right.
Yeah. Okay. Good point. Thanks for reminding me. Yeah. So what is done here in the Olson and Schaefer article, and also by default by Mplus, is to use a log normal distribution here. So not assuming normality for that tail, but assuming log normality, which allow for that skewness.
And that's automatically built in.
Yes.
One data two-part does that.
Yeah, it does that automatically. Although you can change it, you can do other things than that. But that's the automatic. Yeah. Good point.
Can these procedures handle piling up at the top end of the range as well as the bottom range?
Can the procedures handle piling up at the top? Piling up at the top, yes, but not piling up at the bottom and the top, unless you want to do three-part modeling, but then you have to do it by hand. Yeah.
155. Could you explain what covered the book?
Did I what?
Could you explain what coverage you're putting on?
Oh, yeah, okay. Here's a question about coverage. And coverage has to do with the topic of missing data. Coverage means, in essence, for a variable, that it says how big a percent of the sample actually was this variable observed for. And we know that in missing data estimation in general, you want the coverage to be pretty high. If it's low, you rely too much on the model assumptions and too little on the data in your estimation. Now, with two-part modeling, you build in a lot of missing data because whenever U is 0, Y is missing. So you have to allow for a little bit lower coverage. We actually stop people if the coverage is less than 0.1. So this is going a little bit lower to allow for that modeling, to allow for the missing data in Y. So missing data issue.
I
I think I have a time-varying covariate question, but it might be a missing data question. So I've got varying covariates, but they don't match up with the outcome. So I've got a predictor that changes over time, but was not necessarily taken at the same time as
At the same time point?
Yeah. What might you do with that?
Okay, so the question is, what if the time-varying covariates are not at the same time point as the outcome variables?
Or what if some are and some aren't? Could you impute?
That's a good question.
Sometimes I mean, this is not really an answer to your question, but it's adding further information. Sometimes it may be that you don't believe the time-varying covariate at that particular time point affects that time point, but maybe the one prior to it or something like that, in which case you could match them up lagged, wouldn't you say? So if you have some and you don't have some, and you can match them up appropriately due to your theory, does it really matter if you have one at each time point? I guess it does affect the outcome, so it might not.
Well,
yeah, that's.
When you asked the question, I was first thinking about the growth model for the covariate. But if you put that aside for a while, I mean, for growth model, it seems to lead to sort of individually varying times of observations. But as a covariate, as long as you know that the covariate has happened before these measures, but not before those measures, then you can allow the covariate to have an effect of a certain size. Say that you have covariate at time t, lowercase t. Then it can have effect on yt and yt plus 1. But the effect doesn't have to be the same. And we didn't stress that when we talked about time-varying covariates. You don't have to have the effect only from time point from xt to yt. It can be from xt to yt plus 1, t plus 2. And they may be sort of fading or at least different effects in the lagged. So I don't think, if you have it as a covariate, I don't think that it adds any difficulty really, except that you probably want to relax any equality requirements for the parameters of that time-varying covariate. Yeah. Yes?
Slides 111.
111? The advantage of having this is that you allow it to be random instead of fixed. Is that what you mean?
Yes.
Right. So you do allow for a variation across individuals in the effect of this on that. Is that what you're asking?
Yeah.
Right. That is the advantage, that you allow for that variation. You can see how that varies, and you can try to explain the variation, explain who benefits more from the teaching, which you couldn't if you couldn't explain that variation if it was fixed, if it was a regular coefficient.
So if it was fixed, you wouldn't have SCVC. So all you'd be looking at is the fixed effect from mass 7 to course taking 7 and the other ones.
In a way, you're also interested in the variation of the
Right, you're looking at that regression coefficient as having variability and not being the same for each person. And if it has variability, you're wondering what is related to that variability. So it's just I'd say it's a richer model. But random slopes aren't a dime a dozen. A lot of times people want to add like 8 random slopes to their model or something, and probably 1 or 2 of them might actually be random.
But I think this kind of model has probably, in principle, many different applications. For instance, if you have depression as a dependent variable, this could be stressful life events. A certain amount of stressful life events may have different impact on depression for different people. And you might be interested in what the differences are between these people.
So I think the interest here is the prediction of STVC from the 3 inverse.
Right.
Right.
That's
Yes,
what
but
this
I
model
think
has over the other.
even without these, I think it would be a more correct representation of this relationship. It would be interesting to see if you didn't have this, what difference would it make to have this fixed or random to any of the other parameters?
I have one more question. 1, 2, 3.
That's easy.
You said intercept of I equals to 0. Okay, and you do the same thing for variable,
Yeah, so I do a gram mean centering here, and here I choose a growth model parameterization that has that mean at 0, estimating the intercept to be equal across time instead. You had a question back there, yeah.
Yeah, in the previous slide, can that STVC vary across time points?
Yes. Yeah. If you look at the slide before that even, this slide, STVC is pi 2, we agreed. It varies across people, but can also vary across time. But that, if you let it vary across people and across time, it's a more complex model, a little bit harder to fit, and there may not always be enough information in the data to define it, to identify it well.
And if you wanted to do that in the input, instead of having STVC before each of the 4 bars, you would have a different name in front of each of the 4 bars. When you have the same one, it means they're held equal.
You can have STVC 1, 2, 3, 4 here. And you can even have STVC 1, 2, 3, 4, but say that the variances are the same and the means are the same, but it's not the same variable. Now that's subtle. 4 different variables, but perhaps with equal means and variances. That's possible. Yeah, behind you.
Yes, I guess the 1, 1, 3, the last 3 lines in the model. In that 3 lines, we omitted and the model will assume automatically as the same.
Wait, where are you pointing? I couldn't hear.
The last 3 lines.
Last 3 lines?
Yes.
Right.
Can that be omitted and the model will assume automatically?
You mean, is this a default?
Yeah, I don't know.
Is that included by default? Well, I don't always remember the defaults.
Right.
So, what I do, I remember most of the defaults, but not always all of them at all times. So I run it and look at tech 1, and I look at for the output and see if I get those. I see if I get those parameter estimates, and if I don't, I add it. So because I added it, I guess it's not default.
Right, probably because you have type equals
And it's
random.
probably because I have type equals random, and I would urge you to add it.
Yes.
Page 1, slide 155. First two statements in the model from them. Could you just verify what the time scales are?
Oh, this. Okay, so yeah, so this is like it is at the Hopkins data here. Say that this is fall of 1st grade, and this is spring of 2nd grade. Fall of 1st grade, spring of 1st grade, spring of 2nd grade, spring of 3rd grade. So fall of 1st grade is half a step to spring of... Okay, I'm lost. But you understand, right? So it's just the timing, fall, spring, fall, spring.
So the time scores reflect the time.
The distance in time.
Distances.
So regardless of the variable, even though it might be a dichotomous or categorical, it doesn't matter.
Right. So
No, doesn't matter at all. It's just the distance in time. So this distance is 1/3 of that distance, of this distance. This distance is half of this distance. That's how you think. So from fall to spring in 1 year is half of the distance from spring to spring. Does that make sense? That's approximately right? Yeah.
I was wondering what the advantages of doing these parallel models, or having the two parallel, I forget what it's called. Anyway,
Processes.
parallel processes, yeah. Why would you just do 2 main models? Is there some specific advantage, or is it just...
Well, you might want to look at the relationship between the models.
In the
Or, I mean,
diagram
between the
show,
processes.
Like, it didn't look like they were, it looked like they were just sort of drawn on the same diagram, but not
But in the model, you estimate the relationship. If you did them separately, you wouldn't know anything about the relationships among these 4 processes. And it may be that, well, like depression,
Well, for
and what are some comorbidity things?
Yeah, so you here's comorbidity. If your math performance is high, you're likely to grow in your math attitude. So not only can you estimate covariances, but you can actually have this predict this. So you can have arrows from here to here, but also arrow from here to here, from here to here.
And you couldn't get that if you did them separately. And I think sometimes in psychiatry there are more interesting ones that you should know about.
Yeah, no, so aggressive behavior of the child in the classroom and achievement. Very aggressive behavior of the child in the classroom.
Tired and cranky child.
Right. Other questions? Yes.
Just as a follow-up then to that, if you're starting to talk kind of what seems to be about reciprocal relationships, that, you know, if you're used to it before, you said like depression and stressful events, assuming that, you know, depression at time 1 would affect stressful events at time 2, which would then affect depression at time 3, or moving, which model might be more appropriate, or which diagram, for instance, this one, this figure, this one on page 157, or the one on page 111, but then kind of making the arrows go both ways, or neither.
Okay, so if you have 2 processes, would you work with one process as covariates or both as growth models? I think this is the lower ambition model. There's nothing wrong, even if there was a growth in this process, it wouldn't be nothing wrong with using them as covariates. But I think there's a higher level of ambition if you want to look at this model to try to explain the growth. Because this is the only way you could say that the growth in this process is related to the other process. So it's just a higher level of ambition, I would say. And here you really have to believe that it is relevant to talk about the growth model also for the second part that you used as covariates before. Yeah.
In the parallel process growth models, if you introduce covariates, would you still retain the covariances among the latent growth factors?
In this?
You can still estimate.
No, I mean, in the parallel process growth models, when you add covariates,
you still have the residual.
Right, we still have residual
covariates about the late growth and intercept factors.
The residual.
You add covariates, you still retain the covariates.
Yeah.
You just add the covariates to that.
Right. Yeah. So again, there are 3 ways these two processes could correlate, because they're both influenced by X, because their residuals are correlated even beyond X, because you can never bring in all of the covariates. So lots of left out covariates that make them correlate, and that's picked up by the residuals being correlated, or these residuals can correlate. And Linda said that it's the latter that's often forgotten, that these residuals can correlate, and if you leave them out and they correlate highly, the correlations are going to be forced through here, and you're going to get the 2 highly correlated growth factors, and you're going to get the dreaded message, the psi matrix is not positive definite. And that's not good. All right.
I just was wondering on slide 111, I'm wondering how would you request the individual slope estimates from Math 7 on CRS 7 if you wanted to output those, for example, to a file or something? Is that possible?
So you can save the results?
I wanted to save the individual slopes.
Save data has, save data command has I think the results equals, so you can save your results.
The factor scores, I think.
He wants factor scores. I'm sorry. I thought, so in the save data option, you can use the F scores option.
And it would give me the slope estimates for each individual?
Yeah. All of these latent variables are factors in Mplus thinking. So requesting factor scores, FS,
Anything
all you
in
need
a
to do.
circle, you're going to get factor scores for if you request F scores in
Okay.
save data.
Yeah.
I just wanted to clarify slide 109. Okay, so those equations on there, well, go ahead and keep up 111. 109, okay. So those equations, can you point out which parts are level 1 and 2? Which equations, how that merges?
In here?
Yes, with that
level
equation.
1 and level 2 equations?
Yeah, with that model.
Okay, so level 1 are the regressions up here. Now, the 4 outcomes on I and S. So the regression of Y equals,
I, S,
right.
and then STVC, which is the multiplier of the CRS. So all of these, 1, 2, 3 parts, 1, 2, 3, which involves these, are on level 1. So
Okay.
time variant covariates are on level 1,
Okay.
and the rest is on level 2.
And then the rest is that part down there.
Okay.
So it's interesting, level 2, level 2 totally works with these latent variables as dependent variables. So level 2 is totally latent outcomes. And nevertheless, it works. I don't know how, but sure sells.